Hey everyone, welcome to a first video on physics. I'm just going to be going through a little intro problem. I'm interested in expanding my YouTube to a bunch of stuff from, math, computer science, and even physics. And so I'm just going to start it here. So we're just going to get started with this little intro problem here. So I'm going to go ahead and begin with reading the question. John throws a rock straight up at a velocity of 7.40 meters per second. The rock is released from John's hand at 1.55 meters above the ground. Will Robin see the rock if a wall with a height of 3.65 meters is at her eye level? From reading the question, we know we are dealing with just one object moving in one direction. The problem gives us velocity, a starting height or distance in the y-axis, and a final height or distance in the y-axis. The question asks to figure out if the velocity of the rock is enough to go the total displacement, or basically if it goes high enough for Robin just be able to see the rock. Let's start with writing our variables. So the velocity is given. The velocity for the rock equals 7.40 meters per second. The starting height of the rock is also given. The rock is initially thrown at 1.55 meters high. And the final height of the rock is given as well, with the wall being a constant 3.65 meters high. The minimum height the rock basically needs to travel for Robin to see it. The rock is thrown straight up in the y direction, which goes against the acceleration of gravity, which is a negative 9.8 meters per second squared, as acceleration is a vector and has a direction along with the magnitude. To find if the rock reaches past 3.65 meters, first the final distance, or displacement of the rock, needs to be solved for. Let's start with drawing a picture of the problem. First, John is here staring at the bottom of the wall, and Robin is up over here on a little ledge. The rock is in John's hand and is being released straight up at an initial distance of 1.55 meters above the ground. And the rock is also initially thrown at 7.40 meters per second, straight up. Acceleration from gravity will affect this problem because we live on Earth, which is our negative 9.8 meters per second squared. And the height of the wall is 3.65 meters, which is the height that the rock must travel for Robin to see. Let's move on and find the equation we will need to solve the problem. Looking at the equations we know for this mechanical problem, we have the initial velocity of the rock, the acceleration of the rock, the initial height of the rock, and we are looking for the final height of the rock. There is one more hidden piece of information we need, and which we have. I just forgot to write it, and do later. Remember, the rock is being thrown up against gravity, so eventually it will come back down to Earth. With these kinds of problems, there must be a peak where the rock will start to fall, and thus a moment where the velocity goes from up going positive to 0, and then negative, and thus falls back down to Earth. The maximum height is found when our final velocity is 0 up at the air, almost the shape of an upside down parabola at the top. The perfect equation to use with the information we found is the velocity final squared equals velocity initial squared plus 2 times the acceleration times the displacement, or the difference between final and initial distance, of Rx. In this case we are going the y direction, but I kept it consistent with x for this intro video. With the equation, the problem can now be solved for. So let's start with rewriting the equation we need. Since we know we need to solve for the final x value, let's just do some algebra and rearrange the equation, solving for just the final x distance. Then we can just plug in our numbers and have less chance of error. Subtract the velocity initial squared on both sides to end up with velocity final squared minus velocity initial squared equals 2 times our acceleration times the final x minus initial x distance. Now divide 2 times our acceleration from both sides and cancel out those on the right side. Continuing with velocity final squared minus initial velocity squared divided by 2 times the acceleration equals our final x minus initial x distance. Last step is to now add initial x distances from both sides and cancel on the right side. The final equation is velocity final squared minus velocity initial squared divided by 2 times its acceleration, all plus the initial x distance equals our wanted final value of our final x distance variable. Let's just plug and chug now. Remember, our final velocity will equal 0 from going against gravity and thus falling back down. So plugging in, we have velocity final is 0, velocity initial is 7.40 meters per second, acceleration is negative 9.8 meters per second squared, and our initial x distance is 1.55 meters. We continue with 0 meters per second squared minus our 7.40 meters per second squared divided by 2 times our negative 9.8 meters per second squared, plus the 1.55 meters, which will all equal our final x distance. After some calculations, we have negative 54.76 meters squared per second squared divided by negative 19.6 meters per second squared plus the 1.55 meters. Calculating and crossing out our units now, we end up with 2.79 meters plus the 1.55 meters, which equals a total distance of 4.34 meters. So, our final distance of the rock is 4.34 meters, meaning the rock reaches a peak of 4.3 meters high. This is a much greater value than our needed 3.65 meters threshold. Clearly the rock is high enough, so Robin will see it soar through the skies. Thanks so much for watching. Hope this was as helpful for you as it was for me. Hope you come back to learn more exciting material. See you next time.